All right, welcome to the kitchen. Scott Johnson here to do a sixth grade science lesson with you. This week we're going to talk about Newton's first law as we start exploring our laws and our motions and forces. And we're going to look at the first one today. We're going to look at inertia. You know, Newton was a great astronomer, a mathematician, a scientist. He had all kinds of things, but really what he's known for are his theories with gravity and his Mathematica Principia, which he wrote in like the late 1600s, saying 1686, I believe. And in that, he described his three laws of motion. We're going to take a small look at number one today. Now, the first law of motion has a name, and it's called inertia. Inertia basically states that an object at rest will stay at rest, and an object in motion will stay in motion unless those are acted upon by an external force. In other words, you see this Barron County ball? Right now, it's at rest. Now, if nothing happens, if everything stays the way it is, it'll stay at rest until an external force, something of greater value than the weight of that ball, comes along and causes it to move. So in other words, I can take my hand and give it a nudge, and there it goes. So that object was at rest until I applied an external force and put it into motion. Now, once we put the ball into motion, forces start acting against it, because there's always forces that actually hate motion and they want it to stop. As soon as that ball rolled from the table, gravity took over. Now, let's rethink what we think of gravity. Gravity doesn't necessarily pull things down. I know we're used to that, right? If I were to take this ball and let it go, you might say, well, the ball fell down. Well, what's actually true is that gravity pulls things to a larger mass, and that's what Newton proved in his theory of gravity. We see things as falling down. Problem is, though, if gravity actually pulled everything down, we would fall off of the side of the earth. What gravity actually does is gravity pulls things to a larger mass. In other words, I am larger than this wiffle ball, right? And because I have more mass than the wiffle ball would actually be pulled towards me. But you know what would happen. If I let this ball go, it's going to go to the ground, right? So, Johnson, if you're bigger than the ball, why isn't it going towards you? Well, just like you at home, this ball, this board, my own self, we're all on Earth. And Earth has a much larger mass than all of us. And because Earth has a larger mass than all of us, we all get pulled towards Earth's mass. That's why we revolve around the sun every year, because the sun's mass is so large, Earth will not fly off through space. Earth's mass is held by the sun's mass. Okay? There's also a reason to show you this in that on the moon being only 1/6 of the size of Earth, on the moon, you weigh 15 times less, or 6 times less than what you hear. So think about this. If you weigh 90 pounds here on Earth, you would only weigh 15 pounds on the moon. And once again, that's because the moon has much less mass. Therefore, the moon has much less gravity. So when I pushed that ball off the table, gravity immediately started trying to pull that towards the earth. You know, think of it this way. We live on the earth. But the next time you see a globe, I want you to check something out. We live in North America, in the United States. And of course, we actually live, if you look at that, on the side of the planet. You know, there's a little Florida and whatnot, it comes out. Then here's Mexico, and then there's South America, right? And then bring it up and then come out on top, okay? I'll even put Hawaii over here, right? And then over here is the start of Europe. We live right here. If gravity actually just pulled things down, well, then we would have been in trouble a long time ago, because we simply would have been pulled off the side of the earth and out into space we would have gone. Gravity doesn't pull things down. Gravity actually pulls things towards a larger mass. Where we're standing, the largest mass around us is Earth. So think about that. This marker doesn't fall down. No. Earth wants this marker right now. And so what happens is when we let things go, when we jump in the air, even when we get on an airplane that eventually has to land, we used to say everything that goes up must come down. But the truth of the matter is gravity is pulling on you because gravity wants to bring you to the larger mass. If this ball and I were out in the middle of space where there was no air and there was nothing anywhere near us, over the course of some minutes and hours, possibly even days, this ball would get closer and closer and closer to me because I have way more mass than the ball does. Why are there asteroids? In fact, millions of asteroids that hit Earth every single day, most of them no bigger than the size of a grain of sand. Well, once again, it's because as these rocks get so close to our planet, they're actually caught by our gravitational pull and they get sucked into Earth's atmosphere. So an object at rest wants to stay at rest. This toilet paper tube, this egg, this glass of water, they want to stay there and they will stay there until an external force acts upon them. An object in motion wants to keep moving, and it wants to keep moving in a straight line. And it will until an external force is acted upon. Think about this wiffle ball. If we were playing ball and I threw the ball to you, you know, at first it's going to come out of my hand. It's going to be going pretty fast. But then it's going to meet external forces. The first one it's going to meet is friction. Friction, of course, we've talked about this in class. It's when things rub together, right? Well, you might say, well, wait a minute, I don't see anything rubbing against the ball, but there is. It's air. Air is going to hit the ball, and that's going to cause friction. That's going to begin to slow the ball down. You know, when a pitcher throws their ball, it's actually faster out of their hand than it is when it arrives at the glove. And that's because for that full 60 feet 6 inches, the ball is traveling. It's getting hit by air all the way. Millions and millions of molecules of oxygen keep hitting it. Same thing with a quarterback. When the ball is first thrown out of the quarterback's hand, it's faster here. And then the farther it has to travel down the field, the ball begins to slow down. Same thing with a ball that is kicked. Same thing with cars. As you accelerate, you have to give the car more gas. It has to use more energy because it's having friction with the tires on the runway. It's having friction with the air hitting the front of the car. That's why cars have drastically changed their shape more and more to make the cars more round and less boxy so that air gives less friction as it passes by them. And of course, the other force that hates motion is gravity. As soon as I throw this ball, as it travels, it's going to start getting lower and lower and lower and lower. And that's because Earth's mass is larger and it's pulling this ball down. Well, as soon as this ball hits the ground, what's going to happen? Friction. Friction with the ground is going to begin to slow. And so over time, air friction, ground friction, gravity will cause this ball to roll to a stop. Right? We see this all the time, okay? And this is the principle of inertia, Newton's first law. Any object at rest will stay at rest. Any object in motion will stay in motion. Those things will keep on forever and ever, unless an external force stops them. The pitch is thrown, it will keep traveling to the catcher unless you bring the bat and hit it at the right time. The running back comes through the hole, he's going to keep going to the end zone unless you step in front of him and make that tackle. A volleyball is spiked down. It's going to go straight to that floor unless you get there and make the set, the bump, or the save, right? These things we see all over the place, all right? Now, we have a couple of small demonstrations here. First off, take a look at what we have. We have a marker that is at rest on a sheet of paper on top of a cup, right? We're going to put the paper into motion, but we're only putting the paper into motion. The marker is going to stay at rest, meaning the marker is actually not going to come with the paper. The marker is going to fall straight down, and that's because once the paper isn't there to support it, then it's going to be taken on by an external force, and this external force will be gravity. Once the paper is gone, gravity is going to try to pull that marker to Earth, right? And then, of course, down it goes. If the cup wasn't here, if the table wasn't here, the marker would be going to the floor. If the floor wasn't here, it would keep on going lower and lower. Earth's gravity, Earth's mass, is constantly trying to pull you to the center of Earth. Floors, soil, ground, rock, these things keep you from Earth pulling you all the way to the very middle. One other small demonstration, though, we can see is one that you can do easily at home. What I have here is a glass of water, okay? I have a small plastic plate. We use this all the time here to put food for Nolan and Presley on it. I'm just going to put that right there. The dreaded empty toilet paper tube. Oh no! Just putting that there. And here is an Easter egg, a little plastic Easter egg. We're going to put that right on top of the tube. Now what we're going to see here is the exact same thing that we've been working with, right? So we have objects that are at rest. The cup is at rest. The plate is at rest. The tube is at rest. The egg is at rest. But what if I put the plate and the tube into motion? If I apply an external force by smacking the plate, then it's going to go into motion. The plate will go into motion. The tube will go into motion. But guess what? The egg will be left at rest. But it's not going to float in the middle of the air. Gravity is going to take over and allow the egg to drop straight down into the cup, right? Of course. 1, 2, 3. Oh, got a little crazy. A little harder, right? Put it right there and pop. Yeah. So ultimately what we see here is the principles of inertia. An object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an equal or opposite force. We put the plate and the toilet paper holder, we put those into motion, and yet the egg stayed at rest until it dropped down. Okay? Let's try it one more time just for fun. To make sure it wasn't luck. I've always told that you got to do something 2 times in a row to show. Isn't it wild? Even after all these years, you still get nervous when I hit the plate because I'm afraid I'm going to smack the glass and send it flying. You can try this at home. Just make sure you get your parents' permission and don't make a huge mess and don't break anything because then, I'm the one in trouble. But nonetheless, so we're going to put the plate in motion. We're going to put the toilet paper roll in motion. The egg will stay at rest. And then since there's nothing there to support it, gravity will pull it down. A 1 and a 2 and a 3. Right there it is. Once again, if we had slow-mo on the camera, you would see that once this was gone, there'd be a brief moment where that egg would hold and then down it would go. Thank you so much for your time. We're going to be studying Newton's 3 laws of motion. Today's video is all about Newton's first law, inertia. An object at rest will stay at rest. An object in motion will stay in motion. These things will stay true until an external force acts upon them. Could be a force you apply, could be a natural force like gravity or friction. You know what I would love to see? I'd love to see your attempts at home. Set up your own experiment to show me the inertia. Pull a piece of paper out from it or something, allow it to drop. Set up a cup of water and a plate and a toilet paper roll if you want. You can actually use any kind of ball. You could have used a baseball or a golf ball, things like that. Okay. Scott Johnson, fantastic. Good to see you. Miss you guys. Newton's first law, inertia.